Okay. So we started looking at TD learning, right? We looked at TD 0. Yes. So what does TD 0 do for us? Great. Yeah, but it does essentially right, it does evaluation, right? It just gives, given a policy pi, it finds out what V pi is, right, and uses sample backup and bootstrap. So how do we do control? Huh? Use the Q function instead of the V function. That's it. What we do is fix a policy pi and use the Q function and learn the Q pi for the policy, and then max of that, and then you get a new policy and then you go ahead with it, is it? Okay. So that is one way of doing control with TD0, right. So in fact I can do that even if I have V, but with V finding a greedy policy is hard. So what I can do is I can take the Q function, right. So do you want to write down how this is going to look like? What goes in here? What goes in there? Huh? You think so? Okay, so let us, because I put RT plus 1, we have to add the T everywhere, sorry about that. Okay. So instead of S dash A dash I put AT plus 1 T, ST plus 1 AT plus 1. Okay. So if you stop and think about it, what should really go here is right. So if you remember, this is the current estimate, right, that is the target. So this whole thing gives you a error, right. So did I mention TD error in the last class? Right. So this expression that you get in the TD0 update, that expression is called the TD error, right. What was the TD error? RT plus gamma V old ST plus 1 minus V old ST, that quantity is called the TD error. So I said it is some error term. So whatever error term you use in the TD update is called the TD error, and the error term you would use in the Monte Carlo update is called the Monte Carlo error, blah blah whatever you want, but TD error is the more important thing. Okay. So sometimes so the TD error is special enough to get its own symbol, right, delta. So, typically when I say TD error delta without any other quantification, it is the error on the V function, okay. Just more of a historic note. So, wherever I use delta I will define what delta is, but typically delta by itself typically stands for the error on the V function, okay. Good. So, ideally I want this, why? Because I am using this as my target, and what is my target? It is the expected return starting from this point, right, that is the target. Since I do not have the expected return, I am using a sample return, which is what Monte Carlo gave us. I said instead of using a sample return, I will use bootstrapping to correct that return. So, I will use the immediate reward plus gamma times V, right, that gives me the corrected return, right. So, ideally I should be using the return here, but why am I using the Q function here? Huh? Yeah, so why am I using that, just the action I took alone, right. Ideally what I should have used there is expectation over my policy, right. People see this is essentially equal to right, whatever is my current policy, that is expected value of Q old comma ST AT plus 1, where AT plus 1 is taken according to the current policy, right. So, that is V, but instead of computing this expectation, right, I am just taking one sample from that expectation, that is basically what I am doing. So, if I apply this rule often enough, I will eventually compute this expectation.
Pi comma q old q pi comma old q pi comma, under that single policy we are taking this.
Yeah, I mean if you are not updating the policy, it does not matter, right. If you want, you put the pi here, but since I am fixed a policy, I don't worry about it. You should ask me this question in V, okay, it makes more sense, but here there is another reason why I am avoiding the pi, I will tell you in a minute, right. So, V, if you want to use V pi, do not use V pi, that is fine, right. So, this is how we will estimate Q, right. So, you understand why we are putting in this here now, okay. We are putting this here as a estimate for this expectation, right, as an unbiased estimate for this expectation. Everyone with me? Okay, good. So, what do I do now? I run a few iterations of this, learn the Q function, be greedy with respect to that Q function, and I can update my policy and then run it again, okay. That is one way of doing control, okay. There is another way of doing control, well, which is exactly the same way whatever I told you, except that instead of running it for several iterations with the same policy pi, you take one step with that policy pi, update the Q function, and the next time you have to choose an action, be greedy with respect to the current Q function. If you remember, we talked about this in generalized policy iteration, right. You can just take one step, and then next time you can be greedy with respect to just that one update you have done, right. So, you do not fix a policy in this sense, in this case, instead of having a fixed policy, every time you have to pick an action, you just look at the Q function and pick the greedy action. So, this is like running extreme generalized policy iteration, right. So, for every step you just take one step with that policy, for the next step you be greedy with respect to the value function update that you have done, right. You just keep alternating between being greedy and updating the value function, right. You just keep going back and forth, for one step update the value function, next time you be greedy, right. So, putting all of this together, you can actually get a algorithm like this. So, you start off with arbitrary Q function, okay, then So pick an action AT to perform in state ST according to the current Q value, right. So why do I put according to the current Q value? You could just pick a greedy action, but we know from our bandit experience, being greedy always is a bad thing. So you need to do some kind of exploration. So you be greedy a lot, okay, you explore, right. So you can either do this with some kind of a epsilon greedy kind of an approach, right, or you can do softmax, or you can do anything, whatever takes your fancy. Come up with a good exploration strategy, right. So people do Bayesian exploration, and there are many different ways, optimal ways in which to do this exploration. Right. Great. Now okay, apply AT and you sample ST plus 1 RT plus 1, right. You could sample this, if you have a sample model you could just run this through simulation, or you could just perform it in the real world and get the ST plus 1 RT plus 1, right. Now comes the important thing, pick AT plus 1 according to the Q function, okay, the current Q function. Okay. Now what do you do? And keep doing this until your episode terminates, right. Once the episode terminates, then you go back, pick an S naught and keep doing this again and again until you are happy with your Q function. Okay, right, fine, you don't agree? So there is no explicit evaluation stage, there is no explicit greedification stage, right. So the evaluation is done here, right, and the greedification is done here, where here. Okay. There are some small caveats here. So if you want this algorithm to converge to something, right, what do you think you should do?
Decrease the epsilon over.
And then anything else? Decrease alpha also over time, right. So decrease alpha over time, decrease epsilon over time, so that eventually you will stop updating things, but the eventuality should happen a long time into the future, right. So you should explore a lot, right, so that you have sampled every state action pair often enough, and your alpha should not decay so quickly that even while you are sampling it, alpha goes to 0, then there is no point in sampling, right. So alpha also should not decay till you have sampled enough, okay. So both should decay, but should be decaying at a slower, alpha should decay at a slower rate than epsilon, okay. Is it good? Okay. So this is probably the second most popular reinforcement learning algorithm that is used for solving a lot of problems. So this is called, anyone? SARSA. So what's SARSA? Eh? Sounds like a Mexican dish or a dance. Huh? Yeah. So it's the most dumbest possible explanation for a name. Okay. State, action, reward, next state, next action. So you need the next action also before you can perform these updates. Therefore, they called it SARSA. Okay. The name stuck. I mean, and we have Rich Sutton to blame for it. I mean, he came up with the name, not the guys who originally proposed this algorithm. Okay. So they didn't come up with this name. So the guys called Ramari and Niranjan. So in fact, couple of years ago, Niranjan was going to come and spend like a semester here on a sabbatical from England, but then last minute he changed his mind, so he never made it. The guy who proposed SARSA was going to come and spend a semester here, but he didn't come. Anyway, so this is SARSA. Yeah. This is an on policy algorithm. Why? Because I am following this epsilon greedy policy, but I am also updating the value function corresponding to the epsilon greedy policy, right, because I am using the action that was actually taken, right. So if you go back here, this will be the expected value according to pi, whatever pi I am following, right. So only for that is this a sampler, correct, right. Therefore this is an on policy algorithm. Okay. In fact, if you stop and think about it for a second, in fact I can compute this expectation without knowing anything about the world. No, the expectation is only with respect to pi, and the quantity I am taking the expectation of is q pi, right. I know both pi because that is as policy according to which I am taking actions, right, and I know the q because that is a quantity I am estimating anyway. So I might as well compute this expectation explicitly. I do not have to take a sample from for that expectation. Here in fact I can do the exact computation. So this line I can replace with something like this. That is why I said it is computing the epsilon greedy value. Since we are updating for the exploration steps as well, it is actually computing the policy value function corresponding to the epsilon greedy version, epsilon greedy policy, and that is why I also call it on policy, right. So you could do something like this, right. So in this case there are a couple of interesting things here. I do not have to pick an action a priori, right. So here we first picked the action for at plus 1, right, and then we did the updation, and the way I have written the loop, you notice that I am forcing you to take this action here again, the same action you took. I am only saying apply at, okay, I am not allowing you to pick again, right, because if you pick again then you are not on policy anymore, because I used at plus 1 to update here. If I allow you to pick another action, you are not on policy anymore because my value function has changed, right. I will be picking a different action. So this is slightly subtle things there, right. But here since I am taking the expectation, it does not matter. I can go back and take a new action and I can do this, but this also makes this maybe kinda off policy. It sits somewhere in the gray region between on policy and off policy because I am not actually evaluating the action I took, right. Because at this point I am not trying to even build the pi, right. So, it is just have to think about it a little bit, right. So, at no point am I having an explicit representation of a pi anywhere in the SARSA algorithm, right. There is no policy here, right. It is implicitly defined by the Q functions. So, when the Q function changes, the policy is automatically changing, right. But here I am explicitly talking about a pi, so I have to compute this pi, right, and then I have to throw all of this in, and then I can become greedy with epsilon greedy with respect to the new Q function I compute. Therefore, the pi also will change every step, right. So, apparently this has a name, this is called expected SARSA. Okay. Frankly, I never came across this until the second edition of the book, and I had to go back and see if there is actually a paper on this, but Rich also cooks up things for the book, right. All the off policy Monte Carlo stuff that was there, it never used to exist before they wrote the first edition of the book. He just cooked it up for the book. Okay, so like that he might have cooked up this expected SARSA for the book, I am not sure, but yeah, he just likes to add things.